Hello, everyone. This is Yao Lei, and this topic is Tungsten Fabric optimization by DPK. This work is done by my colleague Chen Zhaoyan and Wang Yipeng in Intel. For some reason, Chen Zhaoyan can't come to this conference, and I will instead him to give this presentation. So our topic covers what is Tungsten Fabric, and we have several optimization work for the vRouter-dpdk in Tungsten Fabric. We will introduce this performance optimization work. First, what is Tungsten Fabric? Tungsten Fabric is an open source multi-cloud, multi-stack SDN solution platform. It has a previous name is much more famous, is Open Control, open source by Juniper, and this is the link of Tungsten Fabric. You can get more information from this web link. The advantage of Tungsten Fabric is this is an all-in-one solution. It has controller, it has vRouter, it has configuration, analysis, orchestration interface. It can support AWS, Azure, Kubernetes, Mesos, OpenShift, also some virtualization technologies such as KVM, VMware, or Docker as container. So this can save your workload for all system integration, and you don't have so much tail switch fatigue when you are handling too much components. So this is the typical architecture of Tungsten Fabric. Tungsten Fabric have two major parts. One is the logically centralized controller and a set of vRouters. It has three types of interface. For the northbound, it's REST for API, and for the southbound interface, it's XMPP, BGP, and netconf. BGP will work as the east-west interface. DPK located in vRouter solution. vRouter-dpdk is the vRouter user space implementation accelerated by DPK for performance, and the recent Tungsten Fabric release 5.01 is integrated with DPK 17.11 LTS release. So next we will discuss some optimization in Tungsten Fabric. The first is the CPU cores. When Tungsten Fabric has long history, and we know that several years ago we have limited core per socket. For example, 2014 we only have 12 physical core on Xeon processor. Now we have up to 28 physical core socket. So in early Tungsten Fabric release, it only supports 11 cores because one core will bind to per NIC queue, and it can only support 11 NIC queues. So now we remove this limitation, and we test the performance with 16 cores, and we can see about 30% performance improve. Also, we enlarge the max value of core numbers. Also, in previous Tungsten Fabric solution, it can only use the CPUs on one socket. Now we can use both sockets. Another improvement for performance is for the RSS side. Tungsten Fabric support three types of tunnel technology. It's MPS over UDP, MPS over GRE, and VXLAN overlay network. First, let's think of normally a traditional NIC only support 5-tuple ISS based on source test IP, source test port, and the protocol number. So it's not a problem for MPLs over UDP in Tungsten Fabric because the source UDP port will change according to the inner packet header. So the traditional NIC still can do the receive that scaling for these packets to different queues. But for MPS over GRE, it's a problem because the traditional NIC can't do the RSS for this. So let's see what's the impact for Tungsten Fabric if we can't do the RSS. This is the traditional workload for MPS over GRE packets in Tungsten Fabric vRouter. The first is the packets arrive to the NIC queue. The step 2 is the core fetch the packets from the NIC queue. And the third step is vRouter distributes these packets to different working cores according to the inner ISS result. The fourth step is the forwarding core transmits different packets to the VM. If NIC count to the ISS according to the inner packets header, so the packet will only go to one NIC, and obviously core 2 will be the bottleneck for all the system, for all the performance in this Tungsten Fabric. So if we have NIC can support MPLS over GRE classification, then the step 1 and the step 3 will be accelerated in Tungsten Fabric. So we try one Intel solution, dynamic device personalization. We call it DDP, our Intel 700 series to ISS the packets to the different queues, and we can get about 20x performance gain for MPLS over GRE packets. So if you want to get more information about TDP, you can access this link for more information. So next, Yipeng will help introduce two other optimization work in Tungsten Fabric. Thanks, yeah. Yipeng.
Thanks. Since we have some experience with the RTE hash from Intel Lab, so we decided to take a look at the Tungsten Fabric to see like what we can do about their flow table. Actually, from the profiling we have on different setup of Tungsten Fabric, the flow table lookup part of the Tungsten Fabric indeed takes a lot of execution time. So this is the figure shows like what the data structure looks like of the Tungsten Fabric's flow table, which is called H table, actually hash table in Tungsten Fabric. So it's actually bucket ties the hash table with linked list. So we identify some bottlenecks with this data structure. First, there's no advanced algorithms to reduce the key collision. By advanced algorithm, I mean like Cuckoo hash or hopscotch hash to reduce the hash collision. So when hash collision happens, you just link list after a bucket. So it happens pretty early, like when you need to traverse the linked list. So that's one bottleneck. The second one, actually that's the second one. You traverse the linked list to do multiple memory accesses. That's pretty costly. Third one is there's no bulk lookup to hide the memory access latency. We all know like with bulk lookup you can first reduce the function call overhead, and you also can overlapping the memory access and computation of different packets. So the fourth one is a scalar K comparison. The K could be very long, tens of bytes, and when you compare the keys, it's pretty costly. And multi-core could compete for shared resources. That's another bottleneck. So we try to do some optimizations based on this data structure. First we do is to add a signature table, exactly like what we do with RTE hash. By having a signature table, you don't need to compare the key before you know like a signature matches. So you only compare a small signature, which could be 2 bytes or 4 bytes. This avoids the overhead when you have a K miss. The second one is when you have batching processing, you can do some prefetch and software pipelining to hide the memory access latency. We also double the number of entries per bucket since we have the signature table. Double the size of bucket doesn't introduce too much like iteration overhead, because now you don't need to compare the full K one by one in one bucket. You just compare the signature. By doubling the entry count per bucket, you effectively reduce the hash collision. Other things including using Intel AVX to vectorize the signature comparison, exactly like what we do with RTE hash. And what in our plan is also to use more advanced hashing algorithm like Cuckoo hash, or maybe just replace the current H table with the RTE hash in DPDK. So we have some POC results. We still work with Juniper and MPG team in Intel to figure out the fix bugs and stuff. But we see pretty good performance improvement from our POC. This is a batching processing, mostly work collaborative with our previous colleague Yang Yi. So we know like OVS and VPP and DPDK, they all do batching, but not the case in current Tungsten Fabric. Batching can reduce the number of function calls. You can prefetch the next package when you process the current one. You have better iCache locality. You can do AVX on multiple packets doing the same operation. OVS doing batching, VPP doing even larger batching. So we think like we should do the same thing on Tungsten Fabric. There are some implementation details, like how do we POC a batching from the RX side of Tungsten Fabric. Pseudocode shows like we should prefetch the next packet when we process the current one. Yeah, so that's, yeah, I guess that's the last two slides. Any question? Okay.
Any questions? In that case, thank you very much.
Thank you.
Thank you.